plus man.
Okay, the title of this talk is The Diffusion of Dye Molecules in Spherical Particles. And the particles in which we used were monodispersed polystyrene latexes. Now this work was carried out at Sinclair Laboratory at Lehigh University. And for several years we've been involved in the area of electrophoretic separations. And what we used as test particles for these electrophoretic separations are monodispersed polystyrene latexes. And so for a series of experiments that we did in conjunction with NASA for electrophoretic separations in space, it became necessary to dye these latexes different colors in order to enhance the visual characterization of separation that occurred. And so the idea was if we can come up with particles of different colors, then as the separation progressed, it could be easily visually verified. And so we became involved in dyeing of polystyrene latexes. And the method we used to dye them was essentially a very simple one. We would take an oil-soluble dye and disperse it in benzene, and then emulsify the benzene, and then pour the benzene emulsion containing the dye into the latex. We would then stir that in an open container for, say, a period of 12 to 24 hours. And what we thought was occurring is that the benzene was swelling the polymer latex, carrying the dye into the latex, and then the benzene is being evaporated out of the system, leaving a colored latex. Now this just shows some of the latex we made for the McDonnell-Douglas-Cephas device, an electrophoretic separation device which flew on STS-7. And so we had a latex, a polystyrene latex, which we left white, and then we dyed one red, and then we dyed one blue. And so as you can see then in the electrophoretic separation device, we were able to see that these latexes clearly separated into the three distinct streams. And that just shows their collected fractions. Now, if you have the situation where you have the emulsion, the benzene emulsion containing the dye, coexisting with the polymer latexes, there could be two primary mechanisms that we were considering by which the solvent could swell the latex. The first situation, and the one which wasn't pursued for this model, would be similar to the situation which exists for seeded emulsion polymerization, whereas the benzene would exist as a stable emulsion and then would be solubilized in the water phase and diffuse and swell the polystyrene latex. And what could possibly happen then, as the dye is essentially water insoluble, its solubility is probably several orders of magnitude lower than that of the benzene in the water. But as the benzene is solubilized in the water, it would increase the solubility of the dye. And therefore the dye could also then be carried into the polystyrene latex. Another approach would be that if the diffusion does not occur rapidly enough, or if there's not enough surfactant, let's say, to stabilize the emulsion, what can happen is that the emulsion droplets could coalesce around the polystyrene latex particles. And that's the situation which was modeled here. You'd have the situation where you'd have number one would be the polystyrene latex particle surrounded by the dye solvent phase, and then surrounded by the bulk aqueous phase. And then what we say happens is then the solvent dye mixture would swell the latex particle, and the solvent would evaporate off, leaving the dye behind. Now, this is the diffusion equation, Fick's law for a spherical system, and a complete angular symmetry was assumed. So what we decided to do is we solve this equation for different dye concentrations. Now, the way to prepare these emulsions, we would use the same weight percent benzene to prepare the benzene emulsion as there was weight percent of the polymer latex. Then we would add various weight percents of the dye based upon the weight percent of the benzene, generally in the range from 20 weight percent dye down to 1 weight percent dye. And so we decided to try to solve this equation for various concentrations of the dye. And this equation can't be solved directly as it is because the diffusion coefficient for the solvent into the polystyrene latex is not a constant, it's a function of the concentration of the solvent. And so it became necessary to determine the form of the diffusion coefficient as a function of the concentration. Now, in his book, in Crank's book, Mathematics of Diffusion, they present analytical solutions for the diffusion of material into a planar sheet, a situation like that. We would assume we had a polystyrene sheet in a large die bath. And in a paper by Crank and Clark in the Transaction of the Faraday Society in 1949, they present rate of uptake data for chloroform for polystyrene sheets. Now, the solubility parameter of chloroform is the same as that of benzene, so we assumed that this data would be applicable then to determine the diffusion coefficient as a function of concentration. Now, as you can see here, as the regain, or what was the initial concentration, the initial concentration is increased, the rate of uptake of the chloroform into the polystyrene sheet was also greatly increased. And the solid lines there represent least squares fits of that data. And so from the analytical solution of the diffusion equation for this geometry presented in Frank's book, the diffusion coefficient for the starting concentration C sub 0 can be obtained. This just shows the least squares fit of the diffusion coefficient on the y-axis as a function of C sub 0, which would be the starting concentration of the solvent dye mixture. And it shows that's a least squares fit, and we took it as the form of an exponential fit for the diffusion coefficient. Now, the top integral represents the diffusion coefficient at the initial starting concentration, and if you assume the exponential fit which was obtained on the previous slide, you obtain that second expression for the diffusion coefficient as a function of concentration. And then if that's inserted back into the form of the original diffusion equation, you get the bottom expression, which gives you the concentration as a function of time in the radial direction. Now, that equation was then solved numerically using the numerical method of lines, and we were able to obtain concentration profiles for various dye concentrations as a function of time. And this is a sample of some of the data we were getting. The solid lines show the dye concentration as a function of time, and this is for a 0.15 micron particle. And as you can imagine, the diffusion rate is a strong function of particle size. And part of this is due to a simplification of the model. Since it was assumed that there was one emulsion droplet surrounding each particle, and you had the same weight percent benzene as you had polystyrene, what you were assuming then was that there were an equal number of emulsion droplets for polystyrene latex particles, and so then you're assuming that as you lowered the polymer particle size, you were also lowering the size of the emulsion droplet. And that's not true, because the emulsion droplet size is simply going to be a function of the surfactant concentration and of the power intensity. We use the sonifier, so it will be a function of the sonification energy as well. And then this just shows the diffusion of the dye into the latex for a longer diffusion time. So what we were trying to do was determine how much dye was going into the particles and how long it was taking. This is for a time of 1.3 minutes, so as the final time. So what we were getting was that the dyeing process was assuming very quickly. It was happening very quickly. It was important to determine this to make sure that the dyeing rate, or the diffusion rate, was not competitive with the rate of absorption. Remember, it was a rate of evaporation of the solvent from the system. And so the rate of solvent evaporation wasn't included in our diffusion equation. Now this just shows T sub 0 as a function of weight percent dye. T sub 0 is the time taken for 95% of the dye to diffuse into the latex. And so we were looking towards using some of these latexes that we're making this way as toner particles for various graphic arts applications. We would freeze dry the latexes and then use them for a variety of, say, printing purposes. And so what you naturally want for a system like that, then, you want the maximum possible amount of dye in the system without having any excess. So it was important to determine how much dye you could get into the latex particles and how long it would take. And this just shows how the time is increased with increasing the dye concentration, but still is very rapid compared to the solvent evaporation rate. And this slide shows the depth to which the dye will diffuse into the latex as a function of the size of the latex. So as you go, it goes up to from 22 microns down at the submicron range, and in a given amount of time, the dye will penetrate through almost the entire latex. And so this is a very interesting way to prepare colored latexes in a very short amount of time. And so what we mainly did here was we had a way of preparing these colored latexes which didn't seem to alter the latex properties at all. As determined by transmission electron microscopy, this didn't change the particle size. As determined by electrophoretic mobility, this didn't seem to change the surface charge at all. And so what we were trying to get at here was then some idea of the time scale of the experiment and some idea of the amount of dye that was actually being absorbed by the particle and of the maximum amount of dye we could get into it and the time scale at which this was occurring. So, that's it.
Trying to reverse learning experience to back out.
Excuse me?
Can you speak out? Say that again.
Have you tried reversing it back and forth?
You mean remove the dye from the latexes? Well, we've never taken the latex particles and added more salt to it and tried to extract it, that's what you mean. That hasn't been done. But these latexes exhibit tremendous shelf stability. I have a series that I made about 2.5 years ago. And they're still stable, and there doesn't seem to be any dye precipitating out of the system. So like the dye definitely was not physically absorbed onto the surface, let's say. I don't know if it would be reversible or not.
Yes, ma'am.
Wouldn't that mean that the diffusion equation should contain an extra term for fixation of the dye molecule? It's irreversible chemisorption. I didn't see a term in that. Well, for that in your expression.
Oh, you're correct. And it was assumed, and this assumption may be doubtful, but it was assumed that the rate of diffusion of the dye molecule was the same as the rate of diffusion of the solvent itself. And that's why there wasn't a dual expression. But you're right. What we would probably get would be more dye concentrated at the surface of the particle and not inside, which of course for our application would be better. We're given dye concentration of a higher color intensity. But that wasn't done. It should be done at some time.
Anyone else? Right, well, thank you very much for the presentation. I think we should